All right, so we are very lucky today to have Justin and Kaidi from from the Simon Center coming to give us a talk today about adventures in non-supersymmetric string theory. So take it away, Justin.
Okay, great. Thank you guys for having me. So today I'm going to be telling you about two sort of sets of works that I've had out recently. One is a pair of two papers, which was done in collaboration with Julio Parra Martinez, who's now a postdoc at Caltech, and with Yuji Tachikawa. And the other thing I'll tell you about is some more recent work. So actually the topic of these two sets of works are not entirely the same, but they do have one thing roughly in common, which is that they have something to say about non-supersymmetric string theory. And that'll be the underlying theme of the talk. So by non-supersymmetric string theory here, I don't mean the bosonic string, but rather superstrings which don't have space-time supersymmetry. Okay, so let me begin with just a little bit of motivation here. So back in the mid 90s, around the time of the second superstring revolution, it was discovered that all of the SUSY string theories that we know and love are just different limits of a single underlying theory. And that gave us this famous picture of the duality web, where perturbative type 2a, type 2b, etc., are all just different limits in the moduli space of one underlying theory. And so this is, of course, a great scientific triumph, but it's also, in a sense, a great philosophical triumph. I think that the idea that there exists one underlying fundamental theory is probably appealing to a lot of us. But at least at first sight, this philosophy seems to have some defects. For example, it's long been known that there also exist non-supersymmetric 10-dimensional string theories that, at least by and large, except for some catches that I'll describe in a moment, seem consistent, and yet which remain largely outside of the usual duality web, except for some small exceptions. So some examples of these non-SUSY string theories are most famously the type 0 theories. The type 0 theories are just like type 2a and type 2b, except with a different Gso projection that gives them non-supersymmetric spacetime spectra. There are also some analogs of type 1 theories, so some unoriented type 0 theories. And so the precise number of these was not known in the literature, and we'll come back to this point in a moment. And there are also some well-known non-supersymmetric heterotic strings. Okay, and in particular, there's 7 of them, which we'll discuss today. And there's some others as well. But so the point here is that there exist all of these seemingly consistent string theories, which by and large have not been brought into the usual duality web. And to make things worse, there are also some strings which are intrinsically in lower dimensions, so not just 10D strings and their compactifications. The most well studied examples of these are the 2D cases. So there's some 2D analogs of type 0a and type 0b, some 2D unoriented theories, and there's also 2D heterotic string theories as well. Here I'll bring to your attention the fact that there are 3 2D heterotic string theories. This number 3 here will be important eventually. Okay, so the philosophy that we're going to be having in this talk is that string theory is maybe the unique theory of quantum gravity, and hence, as long as these various cusps in this diagram are actually consistent, they should be brought into the duality web in some way. And we're going to try and flesh out this sort of bigger duality web today. Now, of course, before trying to bring these various cusps into the usual duality web, we have to make sure that they correspond to real, consistent string theories. And one thing which is colloquially said about these non-SUSY string theories is that they're inconsistent due to the presence of some closed string tachyons. Now, there exist some exceptions. To the best of my knowledge, there are 3 exceptions. That is to say, cases without closed string tachyons. But by and large, it is true that these theories have closed string tachyons. And for that reason, people tend to sort of write them off to some degree. But of course, the presence of a tachyon doesn't itself mean that the theory is inconsistent. Rather, it just means that we're expanding around the wrong vacuum. Okay, so usually we're thinking of perturbative string theory as a perturbative expansion around flat 10D Minkowski space. And the presence of a tachyon is just telling us that we should think of it as some perturbative expansion around a different background. As long as there exists one stable vacuum, the theory should be considered consistent and should be brought into the duality web. Now, two things that I should say. So one thing is that these stable vacua, interestingly, could be lower dimensional. They don't have to be 10-dimensional. And what we'll see is that in many cases, they're actually exactly 2-dimensional string theories. Okay, so we're going to find that many of these cusps here actually admit to stable vacua, these 2D theories here, hence providing some connection by means of a dynamical transition from this branch here to this branch here. The other thing
is there any claim that these vacua are unique, or these just the claim is that these are possible stable vacua, but not necessarily the only stable vacua?
Yeah, exactly. So these will just be examples of stable vacua, but there could be others.
Thanks.
Mm-hmm. And the other thing that I should just give as a caveat here is that when I'm talking about stable vacua, I'm really only going to be discussing perturbative stability, so like metastable vacua. And the question of non-perturbative stability will be left to more ambitious future work. Okay, great. So that's actually it for the motivation. Let me just tell you the concrete goal of this talk. So the goal of this talk is going to be twofold. First, I would like to classify the various non-SUSY 10D string theories. And then I'd like to find stable vacua or metastable vacua for each of the tachyonic ones. Now, because doing this in full generality is a bit ambitious for an hour, I'm going to split things up into two parts, each illustrated by means of one example. So in part one of the talk, I'm going to discuss the classificational framework illustrated by means of the example of unoriented type 0 strings. Okay, so we're going to be focusing on this cusp here. And in part two of the talk, I'm going to discuss stable vacua. And here I'm going to be using the example of the non-SUSY heterotic strings. Okay, so this piece here. Okay, so are there any questions on the motivation before we go into part one? Okay, so let's talk about this classificational framework. And I'm going to begin here with a review of something that we all know well, which is the Gso projection. So throughout this talk, we're going to be working in the NSR formalism in light cone gauge. So that means the worldsheet content of our theory is some left and right moving bosons. They're left and right moving superpartners, and there's 8 of each of them. And now to go from the spectrum of this NSR string to the actual spectrum of the physical string, we have to do some Gso projection. So the Gso projection is some projection onto some subsector of the state space of this theory, such that that subsector satisfies various nice things like closure of OPEs, mutual locality, modular invariance, etc. So it's a classic result due to Zyberg and Widden that the Gso projection can be interpreted geometrically, or maybe topologically, as a sum over spin structures. Okay, and in this point of view, the different possible Gso projections correspond to different possible insertion of phases into the spin structure sums. So to illustrate this by means of an example, we can consider type 2a and type 2b. These two theories differ by different Gso projections. And so we can see this by just looking at the Taurus partition function. So here I've schematically drawn for you the Taurus partition function. So, well, I think the notation is apparent, but just to make it clear. So this box obviously represents Taurus partition function. And then these lines that I have inserted represent potential insertions of -1 to the f lines. So if we insert a -1 to the f line, then when I move a fermion along the cycle orthogonal to that line, then I pick up an extra minus sign. So I go from the default antiperiodic to periodic boundary conditions. So this would denote the RNS torus. And likewise, this is the NSR torus and the RR torus. Okay, So in any case, what I've got here is just a sum over spin structure. And crucially, for type 2 strings, I have separate left and right moving spin structure sums. And now what I can go ahead and do is insert some phases alpha into these sums. The different choices of alpha give me different Gso projections. Now, of course, I can't just insert any alphas. There are some consistency conditions that have to be satisfied. And as it turns out, at the end of an analysis, one can find that these alphas have to be equal to, up to an overall constant, just 1 on the NSNS, NSR, and RNS tori. And on the RR torus, I have a twofold choice, plus or minus 1. And it's this twofold choice, basically, which gives us the difference between type 2A and B. Okay, so this is the classical story about the Gso projection. And now I'd like to reformulate this in a slightly fancier, now condensed matter language, which is going to allow us to get a nice classificational framework. Okay, so the language that I'd like to introduce to you is the language of SPT phases, where SPT stands for symmetry protected topological phase. So I'm just going to give a lightning review of what these things are. So an SPT phase for our purposes is just a gapped theory which has a unique ground state on any manifold without boundary. So given some manifold X without boundary, the SPT phase assigns to X a partition function, and that partition function is just an element of U1. Okay, so it's a modulus 1 related to the fact that there's a unique ground state. So the SPT phase takes a manifold X without boundary and spits out an element of U1, but it actually doesn't depend on X itself. Rather, it only depends on the Bordism class of X. Let me recall for you here the notion of a Bordism. So given a manifold X1 and a manifold X2, these two manifolds are said to be bordant if there exists a manifold in one higher dimension. Let's say these were d-dimensional. So if there admits a d plus 1 dimensional manifold which interpolates between the two. That is to say that its boundary is the union of X1 and X2. I can also talk about Bordisms between manifolds with some given structure. So let's say that X1 has structure S, which is the structure group of its tangent bundle, something like spin or pin structure. And let's say that it also has some G principal bundle over it. Then I can talk about Bordisms between two manifolds X1 and X2 with this structure, as long as there exists an interpolating manifold along which these structures extend in some appropriate sense. So Bordisms provide some sort of equivalence relation between manifolds, and then I can talk about equivalence classes of manifolds with respect to that equivalence relation. And such classes form a group, which is known as the Bordism group, and is denoted by this omega here. Okay, so the point here is that SPT phases provide a partition function, which is a map from the Bordism group to U1. And hence, if we want to classify d-dimensional SPT phases protected by some G symmetry, all we have to do is a well-defined math exercise, which is to compute the Pointryagin dual Bordism group. That is to say, the group of homomorphisms from the Bordism group to U1. And there are standard math ways of computing such an object. Okay, so I should say one more thing here, which is that this is for the story I've told you just thus far is for manifolds without a boundary. If you have a boundary, then you can have some interesting gapless edge modes, as we'll see in a moment, and that will change. So in that case, the partition function is not just an element of U. Okay, so I'd now like to illustrate this formalism of SPT phases by means
Can I ask a quick question?
Yeah, please.
So I just got a little lost here where the unique ground state came in.
Uh-huh. So we're going to see that in detail in a moment, but
Okay.
The unique ground state basically comes in due to the fact that this partition function here has modulus 1.
This is a finite temperature. This is what is a real-time partition function. What is this?
This is the Taurus partition function.
Just the Taurus. Okay.
Mm-hmm.
strings.
Well, sorry, it's not that. So you can think of it as the torus partition function in the cases we're going to be looking at, but it's really any closed manifold, Euclidean manifold, will have this property.
Thank you.
Mm-hmm. Yeah. So any other questions? Okay, I'm going to be more explicit about this right now, actually. Okay, so I want to illustrate all of this in an explicit example, which is the example of the so-called Kitaev chain, also known as the Majorana wire. And this system is actually so concrete and explicit that it's been realized experimentally. So people have actually built this thing in a lab. And what's really beautiful about it is, despite being so concrete, it's actually going to be exactly this system which differentiates between type 2A and type 2B. So, so this slide is a blank slide, and I'm going to go ahead and actually just write the slide by hand. I think this is best for pedagogy here. So we're going to see how to construct the Kitaev chain completely explicitly. So, so we can pretend like we are condensed matter experimentalists here. So how would I build this system? So I'd start by just taking a one-dimensional lattice. Okay, let me draw more lattice points, I guess. Okay, let's say we have lattice sites labeled 1, 2, ... up to n. And each lattice site can be either occupied or not occupied by an electron. Okay, so some Dirac fermion. So at the lattice site I have creation and annihilation operators for a Dirac fermion, Fi dagger and Fi. They satisfy the usual algebra. And I have associated to each site an occupation number, Fi dagger times Fi, which is 0 or 1. Now what I'm going to go ahead and do is I'm going to do a formal change of basis of my creation and annihilation operators. So in particular, I'm going to redefine Fi to be 1/2 Ci plus I di, and likewise for Fi dagger. Okay, so I've changed basis now to these Ci and di creation and annihilation operators. And clearly, by their definition, they satisfy Ci dagger is equal to Ci and di dagger is equal to di. So these are now creation/annihilation operators for some Majoranas. And so what we've effectively done by this change of basis is we've split every lattice site up into 2 sites. Let's say this was site 1, this is site 2 up to n. And now we have site 1 split up into 2 separate sites, which can be occupied by Majoranas with respective creation operators C1, D1, and likewise C2, D2, ... Cn, Dn. Okay, and let me note one simple thing, which is that if I rewrite the occupation numbers in terms of Ci and Di, a little bit of algebra just shows that it's written as shown here. And since this thing is 0 or 1, it tells us that Ci Di, this combination here, is plus or minus 1. Okay, so far all I've done is I've written down a lattice and then I changed basis. And now I'm going to write down 2 different Hamiltonians for you. One of the Hamiltonians I will claim describes a trivial phase, a topologically trivial phase. And the other one will describe a topologically non-trivial phase, which will be the SPT phase in question. Okay, so we're going to see this in detail in a moment. So let me begin with the topologically trivial phase. So I'm going to just write down this Hamiltonian and then explain it. So I'm writing down a Hamiltonian that looks like sum from I is equal to 1 to n, Ci di. So pictorially, what this Hamiltonian does is it links this lattice site with this site with this site, and so on and so forth. Now I claim this describes a topologically trivial phase in the sense that this theory has a unique gapped ground state. Okay, so why does this thing have a unique ground state first? Well, it has a unique ground state because the things that is built out of, the CIDIs, I just told you take values plus or minus 1. And so clearly the ground state is obtained by setting them all equal to minus 1. So the ground state is unique and it has a ground state energy minus n. And the theory has a gap because clearly, if I want to go to the next excited state, I have to switch one of the plus ones to a minus one. And so the energy gap is equal to 2, even at infinite volume. Okay, so this Hamiltonian has a unique gapped ground state. Now let me tell you about the topologically non-trivial theory. So here I'm going to go ahead and copy and paste this lattice that I just drew. Okay, and I'm going to erase these. Okay, so the next Hamiltonian we're going to consider looks as follows. Di Ci plus 1. Okay, and so what does this look like? Pictorially, I've linked this to this, and this to the next one, and so on and so forth. Now, this theory describes a topologically non-trivial phase in the sense that now there is no longer a unique ground state. There's actually a twofold degenerate ground state. And the way to see that is as follows. It turns out that these combinations, Di Ci plus 1, also take values just plus or minus 1. So I get the ground state by, again, just setting them all equal to minus 1. And that, sorry, I see I've made a mistake here, a crucial mistake. So this upper index and the sum is n minus 1. So the ground state energy here is minus n minus 1. But the crucial thing is as follows. Because this lattice is not periodic, I do not have a term that looks like this. And this thing can take values plus or minus 1. And so I have two different ground states, depending on if I take plus or minus 1 here, they're doubly degenerate. This theory is topologically non-trivial in the sense that this Hamiltonian cannot be obtained by a continuous deformation from this Hamiltonian, at least not one which preserves the gap on a closed manifold. Okay, so, right, so this is topologically distinct, and the sort of physical hallmark of that, of this doubly degenerate ground state, is these dangling Majorana modes that I have at the edge of the chain. Okay, so it'll be a general feature, a general property that SPT phases have on their boundary some sort of massless edge modes, as we see in this case in the form of these Majoranas. Okay, so this is the lattice version of the Kitaev chain. Now we're of course going to be interested in the continuum version. So let me just quickly sketch for you the continuum version. So I pass from the lattice to now a sheet. Okay, I've added the time direction in. This is like an open string worldsheet, you can think of it as. In fact, we don't have to just look at a sheet, we can look at really any Riemann surface, even without boundary. And now we can talk about the non-trivial SPT phase on this continuum manifold. So I told you before that these were classified by some dual Bordism groups, which was in particular of this form here. Now in the current case, D is equal to 2, because this is a sheet. And the structure S of the tangent bundle is spin. Okay, I'm going to want to put some fermions on this manifold. So this is going to be spin. And finally, we can talk about adding some extra symmetries into the game, but thus far I haven't discussed any symmetries other than fermion number symmetry. So there's actually no other symmetries in play. So the relevant Bordism group that I would calculate is omega 2 spin of a point. And it turns out that this thing is equal to Z2. So the way you interpret this Z2 is as follows. The trivial element in Z2 corresponds to the trivial phase. The non-trivial element of Z2 corresponds to the non-trivial phase. And the fact that this group is Z2 is corresponding to the fact that if I were to stack two of these non-trivial phases up on top of each other, it would turn out that I could actually deform that to the trivial phase, basically because I can add some interaction terms in this way while preserving the gap. Okay, so that is the Kitaev chain. And there's just one more thing that I want to tell you about the Kitaev chain before we get back to string theory. So I told you that on any manifold without boundary, this SPT phase should spit out an element of U1. So let's consider some closed manifold sigma. Then I want to write down an explicit form for the partition function on that manifold. And it turns out it can be written as shown here. So it's some phase, and it's determined in terms of something which is called the ARF invariant. It's not super important what the ARF invariant actually is. For our purposes, I'm just going to go ahead and tell you what it is on the manifolds of interest. Okay, and in our case here, we're just going to be interested in tori. So I just need to tell you the value of this partition function on tori with various spin structures. So it turns out that on the NSNS, RNS, and NSR tori, the partition function is always 1, whereas on the RR torus, it can be -1. And now, hopefully, at this level already, we can see why this is going to be relevant to string theory. If we go back to our Gso projection picture, remember that the difference between type 2a and type 2b was basically the fact that I could insert some phase, and this phase was equal to 1 on the NSNS, NSR, and RNS tori, and was potentially -1 on the RR torus. This value alpha here is taking exactly the same values as this partition function for the ARF invariant. Okay, so that gives us a new interpretation of the Gso projection. Instead of thinking of the worldsheet theories of type 2a and type 2b as the same, and as just doing different spin structure sums with different insertions of some phases, I can instead say, I'm doing the same spin structure sums for both type 2a and type 2b. There's nothing else that I'm inserting by hand, but it's actually the worldsheet theories of type 2a and type 2b that are different. And in particular, they differ by this subtle topological term in the action, this ARF invariant, which you can interpret as saying that type 2a is in the non-trivial SPT phase, whereas type 2b is in the trivial phase. Okay. So let me just repeat exactly those words for the type 0 string. So in the type 0 string, I again have two different versions, type 0a and type 0b, and they again just differ by a factor of this ARF invariant here. Okay, the only difference between type 0 and type 2 is that in the case of type 0 strings, there's only a single spin structure. I identify the left and the right moving spin structures. Okay, and so I can just say the same words that I said before, basically. So I can interpret this insertion as just doing different spin structure sums, or I can interpret it as doing the same sums, but with different worldsheet theories. Okay, and so that finally leads us to the case that I promised to study, which was these unoriented type 0 strings. So these are some unoriented superstrings. So I want to be able to put some spinners on them or pinners on them. So I'm going to go ahead and work with worldsheets with either pin minus or pin plus structure. And now to classify all of the possible Gso projections, I just have to classify all of the possible SPT phases, which are given by these dual Bordism groups here. And these are standard results in the math literature. So this is known to be Z8. This is known to be Z2. And hence, we would expect to get 8 different pin minus type 0 strings and 2 different pin plus type 0 strings. Okay. And they are differentiated by adding some terms in the action. And those terms are given by the generators of the relevant Bordism groups. So something called the ABK invariant in this case, and the good old ARF invariant that we saw on the previous slide in this case. Okay, so we've seen that the SPT phases can be used to classify different Gso projections and hence different string theories. But they're also useful for more than just that. They can also be used to classify the objects inside of those string theories. For example, we can use all of this business about the SPT phases and boundary Majorana modes to give a beautiful worldsheet rederivation of the classic result that stable D-branes in type 2a and type 2b are classified by complex K theory. And we can also give a generalization of this nice K theory classification in the case of, for example, these 8 pin minus strings. And that gives rise to this here, so some very rich spectrum of stable D-branes. Okay, so that's basically all I wanted to tell you in part 1 of the talk about the classificational framework. So we've used this classificational framework to, for example, find these 8 theories. And it turns out that all of these 8 theories are tachyonic. So this now motivates us to move on to the second part of the talk, where we're going to discuss condensation of the tachyon and identification of stable vacua. Okay, so before moving on, are there any questions?
I have a question.
Mm-hmm.
So you did this SPT, I guess, characterization of the type 0 strings and sort of what you can get from that.
Mm-hmm.
And so at the very beginning of the talk, you said you also do this you can do this for heterotic. And did you say also type 1? Or?
So this classification, so this SPT phase stuff,
Mm-hmm.
it can be done in every case, but it has not yet been done in the heterotic case.
Okay.
I'll have something to say about that on the conclusion slide. But
Okay.
for type 1, it has been done. So yes. There.
Cool.
Mm-hmm.
Sorry.
Yeah. So in the type 1 case, you find that there are 2 theories, which one I think sometimes calls type 1 and type 1 tilde. But it basically corresponds to whether you do the orientfold 9 plus or minus projection in type 2b.
Okay, cool.
Mm-hmm. Great. So any more questions?
Is there some way of thinking about this from a pure spinor perspective?
That is a good question. I don't know. Yeah, that's a good question. I'm not sure. I know, for example, I guess from the Green-Schwarz formulation, for example, there would be nothing like this. Basically, because in that point of view, there's no sum over spin structures. But yeah, for pure spinor, I don't know. That's a good question.
Mm.
Thank you. Okay, so so now I want to move on to part 2 of the talk, if that's okay. And here I'm going to be talking about stable vacua, and I'm going to be discussing heterotic strings. Okay, here I'm not going to be talking about SPT phases at all. I'm just going to use some heterotic strings that were already known in the literature. In particular, these heterotic strings are originally due to KLT and contemporaneously Dixon and Harvey. So I'm just going to very briefly review the tachyonic heterotic strings that are obtained in these papers. And I'm going to actually do it slightly differently than was done in these papers. So the way we're going to obtain these theories is as follows. So we're going to go ahead and start with the usual worldsheet content of the heterotic string. So we have some left and right moving bosons, left moving superpartners. And on the right side, we have a bosonic string. So in addition to these guys here, we have 16 more bosons. And I'm going to fermionize them to get 32 right-moving fermions, rather. Okay, so now with this worldsheet content, the most naive partition function that I can write down is, I would just try and write this thing down. So I put a Degenerate function here for the bosons, and then I would just identify the left and right moving spin structures for every fermion. So I just get one sum and 8 factors of this fermion partition function from the left movers and 32 factors from the right movers here. Okay. And so since these fermion partition functions here admit known expressions in terms of just Jacobi theta functions, you can go ahead and plug those in and then get the Q expansion from this partition function. And if I look at the level matched terms in that Q expansion, these would be the first terms that would pop up. So I'd get 32 QQ bar to the -1/2 plus 4032 plus ... And so what this would tell us is that this tentative theory would have 32 tachyons from here, and an extra 4,032 massless fields, which it turns out could be decomposed into 35 components coming from a graviton, and then another 28 from B field and one from dilaton, all in 10D, and an additional 496 gauge bosons of SO32. So this partition function would describe some non-supersymmetric SO32 heterotic string. And now that we've got this guy in our pocket, we can obtain additional tachyonic heterotic strings as follows. We notice that this worldsheet theory has a Z2 to the 5th global symmetry. So this Z2 to the 5th global symmetry is generated by these 5 Z2 elements here. Each one of them just looks like a polysigma 3 matrix times a bunch of 1s, such that the total is a 32 by 32 dimensional matrix. And that 32 by 32 matrix will act on these right-moving fermions in the vector representation. Okay, so because each one of these Z2 elements is just poly sigma 3 times a bunch of 1s, it's obviously going to act as -1 on half of the fermions and +1 on the other half. All right, now I can go ahead and I can gauge n copies of this Z2 symmetry for n anywhere from 0 to 5. And so at the level of the partition function, it's easy to just write down the effect of this gauging. And what I would get is 6 different theories for n running from 0 to 5, which would have this spectrum of tachyons and some spectrum of massless bosons and gauge bosons, and these are the corresponding gauge groups. Actually, throughout this talk, I'm going to be pretty sloppy, so I'm going to talk about things at the level of the gauge algebra without worrying about the global structure of the group, so forgive me of that. But yeah, so you would reproduce these, and these are exactly the 6 tachyonic heterotic strings that have been found in these pioneering works here. All right, so one thing that I want to point out here is that when you do this gauging of the Z2 to the n, you break the SO32 that you had before down to, at least naively without any enhancements, this group here. Okay, so in particular, this SO2 to the 5 minus n is the thing that rotates the right-moving fermions lambda, which are left invariant by the Z2 to the n that we gauged. Okay, and this SO2 to the 5 minus n can be seen in this column here. So here I have SO32, and then SO16, and O8, and then here I would have O4, which is SU2 squared, and here it's O2 from the U1 factor. So the thing I want to point out is that the tachyons always transform in the vector of that SO2 to the 5 minus n. Okay. All right. So so we've identified 6 tachyonic theories, and now I'm going to go ahead and condense the tachyon in those theories and try to find stable vacua.
Does that include O1 for the E8 theory? That is there a Z2 gauge symmetry that the tachyon is odd under?
That's a good question. I think there should be, yes. So in this theory, there exists one fermion which is in the singlet, and there is a -1 action on that fermion. And that's the same -1 that will act on the tachyon. Yeah, so yeah, on the next slide, let me try and say this again, but I think it does. I think indeed, yeah. Good. Okay, so so let's go ahead and condense the tachyon. All right, so here we're going to follow the example of Hellerman and Swanson. Hellerman and Swanson basically did the exercise we're about to do in the specific case of E8. And here we're going to port the results to just these other groups. Okay, so what's the idea here? Well, when I condense the tachyon, I produce a worldsheet superpotential, which is just the tachyon vertex operator here. And so the worldsheet superpotential should be a 1, 0 superpotential. And this tachyon has an index A here, which is the vector index of SO2 to the 5 minus n. So pretty much the only thing I can write down is I take this tachyon and I contract this vector index with the index of the invariant right-moving fermions. That is to say, the ones that were left invariant under this C2 to the n, so that they transformed into the vector of this. All right, so yeah, so in the E8 case, as I was just saying, so here there's no A index, it's just lambda times T, and I think there is a -1 to the -1 action, which acts on lambda, which must also act on T for this potential to remain even. Okay, so upon condensation, we produce this superpotential. And now I want to plug in a specific tachyon profile here and see what happens. So the linearized equations of motion for the tachyon are given as shown here. So this phi that appears here is the dilaton. And it turns out that one solution to this equation of motion, you can just plug in and check, is the following. So I take the dilaton to be a linear dilaton proportional to one of the light cone coordinates, x minus. And then I take the tachyon to be exponential in the other light cone coordinate and linear in some spatial coordinates. So each component of the tachyon is going to be linear in a different spatial coordinate. Okay. So this is some solution to the linearized equations of motion. And also for some magical reasons that I won't have time to describe here, they're also alpha prime exact solution to the stringy equations of motion. So these are actually alpha prime exact solutions. So I can take these guys, I can now plug it into this superpotential, and then I can integrate along the superspace coordinate. And upon doing so, I'll get a scalar potential, which looks as follows. So what are the salient features of this scalar potential? Well, what we see is that we've generated a mass-like term for every one of the spatial coordinates that appeared in the tachyon profile. So remember, each component of the tachyon was linear in one spatial coordinate. So in total, we're generating 2 to the 5 minus n of these mass type terms. Okay, and this mass is proportional to the exponential of this light cone time here. Okay, likewise, we're also obtaining such a term for the superpartners. So as x plus is going to infinity, what's happening here is that the fluctuations along these spatial directions are suppressed. And hence the theory is effectively a lower dimensional theory in dimension 10 minus 2 to the 5 minus n, which is localized at, say, just 0 in these directions. Okay, so what's happening here is we're getting a dynamical transition whereby when we go to late light cone times, the theory becomes lower dimensional. And so for example, for n is equal to 3, 4, and 5, we get a theory in dimensions 6, 8, and 9. Now, you can obtain the spectrum of massless fermions and gauge bosons just by looking at the partition function and explicitly doing the integrating out of these spatial coordinates. And what you'll find is the stuff in this table here. So we've obtained these lower dimensional theories as as dynamical transitions, starting from a 10D tachyonic theory down to these tachyon-free theories. And we can just examine these lower dimensional theories in their own right and do the usual games that we like to play. For example, we like to look at the low energy theories, which correspond to the string theories. So for example, we like to look at type 2 supergravity and ask questions about anomaly cancellation in type 2 supergravity, et cetera. So in the current case, we're not looking at supergravity because these are non-supersymmetric strings. So the low energy theory is some 6, 8, or 9 dimensional theory of gravity coupled to gauge theory. But we can again ask if these theories are free of perturbative and global anomalies. And so, for example, some lower dimensional analogs of the Green-Schwarz mechanism come into play, and it's a fun exercise to see that everything works out. Okay, so we found some stable or metastable vacua in the cases of n is equal to 3, 4, and 5. That is to say, for these three theories here. And now we'd like to do the same exercise for these three theories here. There's one slight caveat. There's one slight difference between those cases and these cases, which is that, at least for n is less than 2, the formula I gave you for the dimension can't be correct, because it would predict that the dimension is negative. So in these cases, what we have to do is just a slight modification of what we did before. Instead of condensing every component of the tachyon, we just condense down to d is equal to 2. So we condense 8 components of the tachyon. And then you would worry that the d equals 2, the 2D theories we get are still tachyonic, but it turns out that in 2 dimensions, the dilaton background ends up lifting the remaining tachyons and making them massless. And so they no longer represent a instability of the theory. So in this way, we actually get 3 2D theories with some spectrum of massless bosons and fermions, some gauge groups. And actually, these 3 heterotic string theories are exactly the 3 2D heterotic string theories that I had mentioned existed in the literature before. So we've provided some sort of bridge between those 2 sort of patches in the big web that I had drawn before. And we've also found, some other lower dimensional string theories in the process. All right. So that's basically it for the second part of the talk. And are there any other questions before I go to conclusions? Okay, so let me just conclude. So in the first part of the talk, we saw that the worldsheet theories of different string theories can differ by some subtle topological terms, such as the ARF invariant. And these terms could explain things like the Gso projections, the different D-brane spectra, and different Oriental foldings allowed in each of these string theories. Okay. Many of the theories that we obtained in this way were tachyonic. And so in the second part of the talk, we asked whether these tachyonic strings can admit some lower dimensional stable vacua. And we found a positive answer in all of the cases that we studied. And in many cases, we saw that the stable vacua are 2D strings that were already known. Okay, now what are possible future extensions of all of this? One thing we could do is something that Daniel mentioned, which is that we could consider adding SPT phases on heterotic worldsheets. This is definitely going to be interesting because if you just look at the order of the relevant Bordism group, it's pretty big. So you would, at first sight, assume that there might be 65,000 different heterotic strings. So either there are many more strings than we currently know, or there's some vast redundancy in this number that's the origin of which I don't understand right now. Another thing we could do is we could consider worldsheet domain walls. So what I mean by this is we could consider some domain wall between the trivial and the non-trivial SPT phase on the worldsheet. And so this would be like a domain wall interpolating between the type 2A and the type 2B string on the worldsheet. And something more down to earth we could do is we can consider revisiting old literature on orbifolds. Okay, so the subject of discrete torsion in orbifolds is something which is very well studied, but we can now go beyond the paradigm of discrete torsion and think of replacing the usual group cohomology classes with now elements of relevant Bordism groups. Okay, so I just want to close with one final sentence, which is that lately a lot of effort is being expended towards the study of non-perturbative string theory. And this is, of course, very well merited and very interesting. But I think even back in perturbative string theory, there remains a lot to be done and a lot of sort of cute questions to ask. So thank you guys for having me.
Thank you very much, Justin. It was a very cool talk. I wanted to ask if anyone had any quick questions. We could. I'm proposing that, I guess, as per usual, we do any sort of quick questions now, take a quick break, and then come back. So yeah, if there are any quick questions.
I have a quick question. If no one else has. Yeah. I remember for some of the 2D matrix models that there had been a proposal by Verlinde and McGreevy of trying to basically go from 10D 2B theory of ND particles and think about a dynamical transition where sort of only the tachyon degree of freedom became light, much light than all the other sort of non-abelian coordinates of these ND particles. And we're basically trying to recuperate the sort of 2D string theory matrix model from sort of that 10D setting in a dynamical way. And I wondered whether you guys had thought of that connection or if there's any connection at all.
Yeah, so that, I think that paper that you're referring to is actually sort of, at least in my mind, the one that started the whole paradigm of stuff that I started talking about today. So I should say, let me go back to this big web that I had. Okay. So I, of course, I'm not the first one to think about tachyon condensation in these strings. So there's the McGreevy paper that you had mentioned previously, and there's follow-up works by many people at the same time. So for example, Douglas, Klebanov, Kudasov, Maldacena, Martinek, Zyberg have some paper, and some paper by these groups as well. And so there they actually worked out, basically by means of what you just said, connections between type 0A and 2D type 0A, and likewise type 0B and 2D type 0B. So in fact, these connections here were well known. And so what I obtained was what I obtained partially is very much inspired by them. So in particular, when I go from unoriented type 0 to 2D unoriented type 0, that's almost basically exactly what they do. So the more novel stuff that I tried to do was to focus on the heterotic strings, and there something interesting happens in the sense that not every stable vacuum is just 2D.
Sorry, yeah, that was clarifying. Yeah, thanks.
Mm-hmm. Thank you.
So wait, so Daniel, are you thinking taking a break and then reconvening, or what's the plan?
I was thinking that we could take a break, use the restroom, get coffee, and then reconvene in like 5 minutes or something. Okay,
good. Yeah, it's Justin, I'll say that was a great talk. I really enjoyed the talk.
Thank you.
And I'd like to ask some questions. And there's unfortunately another meeting coming up at 2:40-ish. So, but that'll work for a quick discussion.
We'll let you go first, Sav.
No, right. Well, okay.